Give it back.
Good! Woo! Today we're going to talk about Hamiltonian cycles and Hamiltonian circuits. Some people just call them Hamilton. So say whichever one you want, I don't care. What is a Hamiltonian circle? Cycle. What did I just say? Yeah, good. Starting strong is right. Wait, which is which again? Let's just quickly define these things. Hamiltonian. I just forgot all my vocab again. A Hamiltonian. Well, okay. A circuit. A circuit is a closed trail. This man is exactly right. So wait, hold on. Let's just do a little bit of this. Good. Modeling the learning process. So if this is like V1, say, then and supposing these edges are connected like so, then an example of a circuit would be like cha-cha, 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 ending here at V1. Is everyone following the string of these arrows? It's actually a little bit ambiguous because you had to be watching me while I did it, but the general flow was like figure 8. Does everyone agree that that is a circuit? Because, as my own student reminds me, a circuit is a closed trail. And a trail, ET for VP, is a walk which does not repeat any edges. Cool? The distinction between a circuit and a cycle is that in a wait, hold on. Have I screwed this up already? No. ET for VP. So wait, a trail doesn't repeat any edges. Fact.
No, a path repeats no vertices.
Oh my god. Wait, hold on. Good, getting this all on video. Good. Okay, wait. What are all the words again? Walk is just a walk.
Walk is just a walk.
ET for VP. So a trail. It is certainly true that a trail does not repeat any edges.
A path does not repeat vertices.
A path does not repeat any vertices. Yes, that's right. And so we are interested in vertices at the moment. And so what we can say is a circuit is a closed trail. And a cycle is a, wait, I did all this actually on the board last time. So I don't know why I find this so hard, but here it's vertices everywhere. So this actually isn't a circuit then, right? Because it's,
No, it is.
oh yeah, because it's ETV, it repeats no edges. Good. So yeah, so this repeats no edges. All right. What makes a particular circuit Hamiltonian is that it also uses every vertex. Good. So a Hamiltonian circuit is, so just to define this, it is a walk which does not edges. Wait, why do I feel like we're somehow getting this wrong?
I think we are
getting this wrong also.
Yeah.
Wait, it's so.
We didn't talk about
Okay,
Hamiltonian
I can read the book.
Yeah, wait, hold on. Wait, pause. Woo! Hold on. Yeah. It's just, Hamiltonian circuit's just not even a thing. Hamiltonian trail. No. Hamiltonian path. Were you trying to tell me that 5 minutes ago?
Yeah.
Good. We are making so much progress. Hamiltonian path versus Hamiltonian cycle. Good. Okay. What's an example of what's a Hamiltonian path? A Hamiltonian path is a path, ET for VP. Built into the definition of path is that it does not repeat vertices. So it's just any path that doesn't repeat any vertices. So this was just all crap.
Hamiltonian
Hamiltonian path
uses every vertex with no repeats.
Use every vertex.
Sorry. So built into the definition of path is that you don't repeat vertices.
Every vertex.
Hamiltonian means
Hamiltonian means that you also use every vertex.
Yes.
Good. So a Hamiltonian path is a walk that doesn't repeat vertices, and uses every vertex. All right, that only took us 7 minutes. What's a Hamiltonian cycle?
It's a cycle.
It's a closed Hamiltonian path, essentially, in which the only repeated vertices are the first and last one. Okay, good. All right, and what we talked about last time is that there are two kinds of graphs sitting on this sort of extreme of obviously Hamiltonian and obviously not Hamiltonian. So the obviously not Hamiltonian is, what would be an example of a graph which is surely cannot be Hamiltonian? What's one feature?
Disconnected.
Disconnected. Disconnected graphs are not Hamiltonian because the entire point of a Hamiltonian path or a Hamiltonian cycle is that we visit every vertex, and if the graph is disconnected, we can't do that. Yeah? Say yeah.
Yeah.
Okay, then there is the obviously Hamiltonian extreme.
Fully connected.
Fully connected graph, so like a complete graph, like K5 say. And so the basic idea is your graph is Hamiltonian if it's like very connected. The more connected your graph is, the more it has a chance of being Hamiltonian because the goal is to visit every vertex. And so the more edges there are, the more choices you have for what vertex to go to next. And if your graph is completely connected, then any path, all paths are available at all times, so you can just go however you want. Start at one vertex and just go till you visit them all exactly once. Cool? And you can also always get back again. Okay, how are we doing? Back on track. Woo! Well, what we would like to do is determine under what conditions. Oh, and there are sort of just like some obvious applications of this. Like, when would you care a lot maybe about the existence of a Hamiltonian path? Like, this is like practical things. You're trying to.
You're a traveling salesman. You want to.
Yeah, you're like a traveling salesman. You're delivering the mail between various cities, and there may or may not be highways connecting those cities. And also, you're committing so many crimes as you go that you don't want to repeat any highways that you've already been on because you're just, as you're driving from one town to the other, I mean, there's just like a lot of slow cop cars following you. So you can never repeat any routes that you're taking, and you need to rob 5 banks all in a row. And so you need to know whether that's possible. And then a Hamiltonian cycle would be where you go back to the first bank that you robbed, and
You get caught in the last city and they take you back to the first city.
they get caught in that city. Yeah, good. All right, I do not condone bank robberies for the record. Good. Well, yes.
Wouldn't that be a Euler path as if you're robbing, if you can't go back on the edges?
You can't go back to the city.
But you can't go back to the cities.
Oh,
because
he's right.
you're robbing
Okay,
banks.
let me fix up my dumb story about bank robbing. Yeah, so here we go. Here are the 5 cities. I think you're exactly right. I think I messed up my.
Exactly right.
Yeah. So it's like this. You have 5 banks. The banks are, V1, V2, V3, V4, and V5, and there are roads. These are in 5 different cities. And some of these have these are very small towns, just like a bank. That's the whole town. And so the question is, there a way to visit all the banks in such a way that you don't ever go back to that town again? I think that's right. Yeah.
Yeah, that's right.
A walk that doesn't repeat any vertex. Yeah, and use a vertex. So good. So we want to make sure to rob all banks. Okay, good. All right. Here we go. The theorem from last class that let G be a simple graph. In theory, we should be able to go fast with the beginning part because it's like what we did last class. With n greater than or equal to 3 vertices. And I made a claim. Gossett made a claim, which is that if let G be a simple graph with n greater than or equal to 3 verses. And here was the claim. First we defined this notation, delta. Delta was, if you consider all of the degrees of all the vertices, it was like the minimum of that. So take the minimum across all the vertices in V of all the degrees of all the vertices. In other words, D is the number of friends of the person with the fewest friends. Cool? And the theorem says, if delta is greater than or equal to n over 2, then G has a Hamiltonian cycle. So we can start with one friend. Let's move away from the bank things, because it's more awkward to talk about cities being friends with each other. But I guess we could. I don't know, whichever one you like. But if you think about it in terms of friends, you have a whole bunch of people, and one person sort of tells a secret, and asking whether there is a Hamiltonian cycle is equivalent to asking, is there a path through all of these people, following the friendships that they may or may not have between them, such that the secret can go all the way around, and each person can hear the secret once, and then the secret can go back to the original person. Cool? Whoa. Okay, good. Now, note that this is not a complete characterization of the existence of a Hamiltonian cycle. It is merely a sufficient condition for a Hamiltonian cycle. In other words, even though this condition might not be met, there might still be a Hamiltonian cycle. But if this condition is met, then there will be one. And this also should be logical because if everyone kind of has a lot of friends, then the more friends everyone has, the more chance there is for a Hamiltonian cycle. This is all the stuff I said last time. Cool? Okay. And then I made a claim last time, which I didn't bother proving because I was running out of time. I might as well have just done that and stopped. Which is, if, so this is like a lemma, I guess. If delta is greater than or equal to n over 2, then G must be connected. Okay, this is on the one hand sort of, well, I don't want to call it obvious because I actually don't think it is, but if you start sort of drawing pictures and thinking about it, this is sort of very plausible. That you sort of couldn't, that this is a lot of friends for everyone to have. And if everyone has this many friends, if even the person with the fewest number of friends is friends with half of the vertices, then it's impossible for your graph to be disconnected. But let's prove it. And actually, doing the proof out sort of properly is a good, I think, is a good practice. So suppose, for the purposes of contradiction, that no, not for the purpose of contradiction. Suppose, let's take the supposition in the antecedent that delta is indeed greater than or equal to n over 2. Suppose, for the purposes of contradiction, suppose that G is disconnected. And I'm going to show that this leads to a contradiction. And since this leads to a contradiction, I know this graph is connected, and thus I don't need to put connectedness into the antecedent of my theorem. Everyone with me? Okay, so why is this true? Well, if this graph is disconnected, then what can we say? Well, then G has at least 2 components. Now, what's awkward is, if I want this proof to be extremely general, I can't just say, oh, it has 2 components or 3 components. I need to have to say it has some number of components, and I don't know how many. So that makes the sort of technical details of the proof, in my opinion, much harder, because I have to sort of not know how many components there are. I have to say there are at least 2 components. But let's call these components C1 and C2. All right, well, so I have this kind of, well, I guess I could draw a picture. I have this component here, C1, and this component here, C2, and possibly other components. Well, each of these components has some certain number of vertices. I don't know how many. So let's introduce some notation for that. Let the size of component C1 be N1, and let the size of component C2 be N2. Okay, so what can I say about the relationship between n1, n2, and n? Well, if you add n1 plus n2, that's certainly less than or equal to n. It would be equal to n if there were precisely 2 components, but less than n if there are more components. Agreed? Say agreed. That's pretty clear. Okay, good. Woo! Well, okay, now take an arbitrary vertex v1 in C1. So take v1 in C1. Well, okay, here's what I know. I know that the degree, based on my assumption, I know that the degree of v1 has to be, well, greater than or equal to n over 2. Right? Because that's the assumption built into this whole thing, that everyone's friends with at least half the vertices. Okay, but the whole idea of a component is that it's the set of vertices that are all connected to each other, and all of those vertices in any component are disconnected from the vertices in any other component. So what is the maximum number of sort of, well, let's put it this way. So what, oh, okay, I guess this is another way of putting it, right? So the degree of v1 is greater than or equal to n over 2. So v1 must have an edge, with at least n over 2 other vertices. That's simply just the definition of degree, right? But v1 only has edges with vertices in the same component. Right? Okay, so if the degree of v1 is greater than or equal to n over 2, and so v1 has n over 2 edges with n over 2 other vertices, then what can I say about the size of n1?
It's at least n over 2 plus y.
Or rather, sorry, the size of c1, I meant to say.
It's at least n over 2 plus y.
Yeah, that's exactly right. So n1 has to be greater than or equal to n over 2 plus 1. The plus 1 comes from the fact that v1 can only be friends with people in his own components, and at most v1 can have an edge with every other vertex in C1, right? But if v has an edge with every other vertex in C1, then there need to be, then there are n over 2 other vertices in C1, but then there's one more for n1. I could say that a little bit better. Do you want me to try to say that again, or is this clear? It's clear? The total number of vertices in n1 is at least all of the vertices that v1 has an edge with, also in component 1, plus v1 itself. Maybe that's the clearest way to put it. Okay, well, so I'll even just write, right? Since v1 is in C1 also. And this is a simple graph. Okay, well, similarly, n2, I guess I should do it again, right? So v1 is in C1, take an arbitrary v2 that's in C2, so let that be v2. Similarly, I know that for an arbitrary vertex v2 in C2, that its degree, it's also true that, just adding this in up here, that the degree of v2 is greater than or equal to n over 2, again by assumption. And so how many, if v2 has n over 2 edges, or there are n over 2 other vertices that v2 has edges with, then there have to be in C2 at least n over 2 other vertices plus v2 itself, and possibly more. So what I can say for sure is that n sub 2, the number of vertices in component 2, is at least n over 2 plus 1. Cool. Okay, and now what do you want to do with these two inequalities? Add them, and when you add them, you get that n1 plus n2 is greater than or equal to n plus 2. Okay, but these two boxes over here are just clearly contradictory, right? If you combine these two boxes together, you get like, you know, oh boy, n plus 2 is less than or equal to n1 plus n2, which is less than or equal to n. And that's the kind of very satisfying contradiction that you want to say is just not true. Okay, who's with me?
Yeah.
That was a very thorough proof that at least this sufficient condition on on friendships, on connectivity, on the degree of the vertex, assumes that is enough to imply that the graph is connected. Okay, so now we get to the real part of the theorem. So what I want to do is, this is what we started to do last class. Take n greater than or equal to 3. And now, what I'm going to do is, this is very sort of, I think it's kind of high level. I define this set called S sub n to be the set of all graphs G such that G has n vertices, delta is greater than or equal to n over 2, and G has no Hamiltonian cycle. Okay, and what we've done here, and recall that the entire theorem is that every simple graph, for any simple graph with n vertices, if delta is greater than or equal to n over 2, then G does have a Hamiltonian cycle. And so what I'm doing, in order to prove that all the graphs that meet this condition have a Hamiltonian cycle, I'm taking the set of all graphs that don't, and I'm going to show that it's empty. Everyone feel it? Okay. So the goal, this is so far exactly a repeat of what we did last class, the goal is to show that this set is in fact empty. Okay, and our method for showing that this set is empty is kind of very interesting because we're sort of quantifying over all kinds of different graphs, right? Who knows how many vertices? So I've sort of let n be arbitrary first of all, and then I'm not sure how many edges there are. I'm not sure anything. Okay, so then we pull this move. We say, okay, look, this thing is finite, right? S sub n is a finite set because, as we discussed, once you fix the number of vertices, then there are only a finite number of possible graphs on that set of vertices. Because for any two vertices, they're either connected or not, right? If you imagine 15 friends, there are only a finite possible number of graphs on those finite friends. And what we said actually last class is that it's 15 choose 2 is the number of friendships among those 15 people. And for every one of those friendships, it can either exist or not. And so it's 2 to the 15 choose 2, which is a huge number, but it's finite. Okay, so since S sub n is finite, we may choose the graph in S sub n with the most edges. And call this graph G. Okay, and if there's a tie, pick arbitrarily between the two, it doesn't matter. Okay, so what is G? G is I'll even write this down. So here's what we have. So we have this graph G. What is G? Well, it's a set of vertices and edges. Also, G has n vertices. That's another fact about G. Each vertex has degree greater than or equal to n over 2, because that's part of the assumption of the theorem. Also, G has no Hamiltonian cycle, because every graph in S of n has no Hamiltonian cycle. But what I have done by choosing the graph among the set with the most edges is I've basically said, let G be the biggest possible graph you can get that meets the condition and that doesn't satisfy the conclusion. And so what I can say is that if you add even one more edge to G, it has a Hamiltonian cycle. I'll add one more thing before I say that. Also that G is connected by the lemma on the opposite board. Can I get a yeah on that?
Yeah.
Because the lemma on the opposite board showed that if it meets this condition that delta is greater than or equal to n over 2, then it is guaranteed to be connected. But here's the crucial thing. By the way we have constructed this graph G, if we add even one more edge to G, it will have a Hamiltonian cycle. And that's because G was the graph with the most possible number of edges that still didn't have a Hamiltonian cycle, among all the graphs that met the condition in the first place. If you add one more edge to G anywhere, then what you'll get is a graph with more edges than G has. And then it can't be in this set, right? Because we picked G to be the one with the most number of edges. And if you're not in this set, then it must mean you have a Hamiltonian cycle. All right, good? I think the logic here is quite complicated. All right, so what else is on here? Okay, good. Now this is pretty much where the bell rang, right?
Yeah.
Okay, so a couple more things. If G is complete, it has a Hamiltonian cycle. Agree? By duh. We talked about this. And therefore, we can say for sure that G is not complete, right? So G is not complete. Therefore, there must be two vertices which are not adjacent. Okay? So we have two vertices which are not adjacent. Call them W1 and Wn. Okay, good. So, good. Well, now we say, okay, let's define a new graph called G prime. G prime is just like G, but with this edge added. Let G prime be just like G, but with added edge W1, Wn. Okay, if you want to get more technical about this, I guess G prime is just like G. G is a set of vertices and a set of edges. The set of vertices of G prime is the same as the set of vertices of G, but the set of edges is like the edge, like union, this like new edge, W1, Wn. I don't know if anyone wants that written out like that, but there it is. Okay, so what can we say about G prime? Well, of course, I'll say a bunch of things that are obvious. G prime has n vertices. That's true. Also, G prime meets the condition, right? G prime satisfies the condition that delta is greater than or equal to n over 2. In fact, I added an extra edge, so everything has even more. The degree, went up at least somewhere, but it certainly didn't go down. Okay, and G has one more edge, or G prime has one more edge. All right, what's the conclusion? I mean, I sort of said all this already a few minutes ago.
So G prime is not in S of n.
G prime cannot be in this set S of n, right? So G prime is not in this set S of n because G is the member of S of n with the most edges. And G prime has one more edge. Who's with me? Okay, and therefore, all of this was really just to get to one conclusion, which is that G prime has a Hamiltonian cycle. And I can say even something else about this Hamiltonian cycle in G prime. It must use the edge W1, Wn. And the Hamiltonian cycle in G prime must use the edge W1, Wn. Because if somehow this Hamiltonian cycle in G prime didn't use the edge W1, Wn, then that very same cycle would exist in G. But by assumption, there is no Hamiltonian cycle in G. Okay. How are we doing? There's like a lot of like quantifier manipulation and logic setup, all to get us to this this point, that there is in G prime this Hamiltonian cycle, and here's what it looks like. It looks like W1, W2, W3, and then et cetera, et cetera, et cetera. And okay, so there's some arbitrary member, WK, WK plus 1, la 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 la. Eventually, you get to, so dot 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 again, Wn minus 1, and then Wn, and then finally W1. Okay, is all of this really necessary? Yeah, kind of. What's going on again? Let's just to talk this out. This Hamiltonian cycle, what's a Hamiltonian cycle again? It took us 7 minutes to remember what the hell this was. But it is, it uses every vertex and does not repeat any vertices. Yeah, but, so essentially, it starts at W1. Well, I guess it doesn't start anywhere, is one way of thinking about it, right? Because a cycle is a cycle. One nice thing about the Hamiltonian cycle is like, you could pick it up at any given point, right? It doesn't really it's not really said to be started anywhere per se. I think of it as starting here because this was the magic edge. I'll do it in blue. This was the edge that made the Hamiltonian cycle possible, right? Without this edge, W1, Wn, we would just have graph G, no Hamiltonian cycle. But suddenly, with the addition of this edge, W1, Wn, a cycle is possible. And what does the cycle look like? It goes W1, W2, and this edge must get used. Cool? Okay, so this is where the proof starts getting serious. So I'll just even label this. This is the Hamiltonian cycle in G prime. Okay. Well, once we see that this is what the Hamiltonian cycle looks like in G prime, and once we observe that this special extra friendship that G prime has, that G doesn't, was essential for this Hamiltonian cycle to exist, then the following can't happen. So this is impossible. It's impossible to somehow like do a Hamiltonian cycle that doesn't involve this edge. Well, what would a Hamiltonian cycle look like that doesn't involve this edge? Well, it might go like W1, W2, W3, la 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 la, WK. Well, one way that Wn must get visited.